So moving on along to 10.2, we're going to do more operations with matrices. Just out of curiosity, any idea how to tell if two matrices are equal? They're the same. Okay, yeah, that's seriously it. We're going to talk about adding and subtracting matrices. You can't add and subtract any matrix. Certain things have to be true. We're going to do multiplying matrices, talk about multiplying by a scalar. What's a scalar again? We've talked about scalars before. No. What's a scalar? It's just a number. So if I take a matrix and multiply it by a number, I multiply every number inside the matrix by that number, by that scalar. It's not a big deal. We're going to multiply two matrices together. And certain things must be true in order to multiply matrices. And then real life problems, i.e. word problems. Yay. Okay, they spent a lot of time talking about equality of matrices, but Teddy's already told y'all what it is. If they're the same, then they're equal. Okay, and that's what all this says. There's a rich mathematical theory of matrices and its applications are numerous. This section introduces some fundamentals of matrix theory. It is standard mathematical conventions to represent matrices in any of the following three ways. So the three ways we can represent matrices. We can represent a matrix by simply using a capital letter. Matrix, capital A. Matrix, capital B. Matrix, capital C. We can denote a matrix by using a letter and two subscripts indicating the number of rows and columns. A sub ij, B sub ij, C sub ij. We can do a matrix by drawing a matrix and showing you all the inputs in the matrix. Okay, wonderful. Who'd have thought? Two matrices are equal if they have the same order. The dimensions have to be the same order. And every entry within the matrix must be the same as the other matrix. Okay, that was fun. So here are two matrices that are equal to each other. What is the value of A sub 1, 1? 2. What is the value of A sub 2, 1? This is too difficult. All right. So obviously, you can tell by looking at these matrices, the corresponding cells must be equal in order for the matrices to be congruent. Matrix addition. In this section, we're going to do three basic operations. We're going to talk about addition, we'll talk about scalar multiplication, and we'll talk about multiplication. With matrix addition, you can add two matrices, but only if they have the same order. I can add a 2 by 2 and a 2 by 3, a 2 by 2 and a 2 by 2. I can add a 2 by 3 and a 2 by 3. I cannot add a 2 by 3 and a 3 by 2. Because in order to add matrices, you add like positions in the cells. That make sense? Okay. So what would the answer to A be? Or can we do it first of all? Can you add a 2 by 2 and a 2 by 2? Orders are the same. Perfect. So what's the answer? 0, 5, -1. Okay. Yay. We applied 4th grade math. When did negative numbers start? Do you remember? Does 4th grade sound right or later? Maybe 5th grade? All right. How about the answer? Or first of all, can we do B? 2 by 3, 2 by 3? What's the answer? Okay, the same as the first one. Any idea what this matrix might be called other than the zero matrix? A null matrix. What else? Do what? What do you have to add? It's not empty because there's stuff in it. Identity, right? It's identity. What Add to yourself to get yourself, you add nothing to yourself to have your own identity, right? What do you add to 6 to get a 6? You add 0. So 0 is the additive identity. This is the additive identity in a matrix form. Can we do part C? Can we add those? Yes. What do we get? Which makes, in part C, these two matrices are additive inverses of one another. Remember, if we take you, if I did, what kind of a matrix is this first matrix here? 1, -3, -2. What kind of a matrix is that? It is a 3 by 1. What else is it? Remember, mathematicians aren't very smart when it comes to naming stuff. It's very obvious. Is that a row? This is a column matrix, right? A column matrix. Just throwing some stuff out there we talked about. Any problems here? Okay. In operations, wait, I think I skipped. I think I'm supposed to slide down. Yes, I skipped one. Okay. Let's add A and B together. Do what? Oh, we can't do it? No, I can't do it. It's not defined. We have what's called a dimension mismatch here. Remember, to add and subtract matrices, the dimensions have to be exactly the same. We don't talk about subtracting matrices. Instead, we the opposite, right? We take a matrix and multiply it by the scalar -1, and then we add them. Go. In operations with matrices, numbers are usually referred to as scalars. In this text, scalars will always be real numbers, so we're not going to take a matrix and multiply it by an imaginary number. That's not cool. You can multiply matrix A by a scalar C. I want to point out, notice that the matrix is still a capital letter, right? But the scalar was denoted by a lowercase c. That's just a number. By multiplying each entry in A by C. And we could write that as lowercase c, capital A. That means take lowercase c and multiply every member of the matrix A sub ij by that number c. The symbol -A represents the negation of A, which is the scalar product of -1 times A. Moreover, if A and B are of the same order, then A minus B represents the sum of A and -1B. That is, A minus B is equal to A plus -1 times B. It's often convenient to rewrite the scalar multiple CA by factoring C out of every entry in the matrix. So look at this matrix to start with here. A matrix full of fractions, kind of messy. And if you were writing that, especially with some of your writing, it gets even messier. But I noticed that every one of these cells contains a denominator of 2. So I could actually factor out a 1/2. So instead of multiplying by a scalar, I'm going to take the scalar away. So if I divided every one of these things by 1/2, I would be factoring out the 1/2. So I could rewrite this matrix as 1/2 the matrix containing 1, -3, 5, and 1. Is that a little cleaner? Okay. Are they equal? Yeah, it's exactly the same thing. Okay, properties. They're similar to properties that we've used in just regular real numbers. I can take two matrices and add them together. I don't care if it's A plus B or B plus A. It's the same answer. That is the commutative property of matrix addition. I could change the groupings. A plus B plus C added together is the same thing. A plus B added together and then add C to it. The associative property matrix addition. If I had two scalars multiplied by a matrix, I could either multiply the scalars together first and then multiply them by the matrix, or I could multiply the matrix by one of the scalars and then multiply by the other scalar. Same thing, the associative property. We've already talked, no, we didn't. Identity property, that's multiplied by 1. Any idea what the matrix identity looks like? I don't remember if this actually goes into detail on it, so I'm going to write it down real quick. That's not even close to right. I can't even spell identity. Huh?
If you needed like that help. You just need to add a few letters. Yeah. Yeah. There you go.
Where is, oh, it's right there.
Yeah, that's
Okay.
where I was pointing.
Okay, the identity matrix,
You spell matrix.
shut up, it's going to be a square matrix always. Okay, so the 1 by 1 identity matrix looks like this. The 2 by 2 identity matrix looks like this. What's happening? The 3 by 3 identity matrix looks like this. Yes. Okay, so the identity matrix just has a main diagonal of 1s and everything else is 0s, but it's always square. Okay, so if I take the identity matrix, and that's not even showing here. If I take the identity matrix and multiply it by matrix, I get what I started with, and it doesn't matter which side I put the identity on. Distributed property. If I had two matrices added together, multiplied by a scalar, I could multiply each of those matrices by the scalar. Or if I had the sum of two scalars multiplied by a matrix, I could distribute that matrix to each of those two scalars and then add those together. Assuming, well, they're both matrix A, so they're going to be able to add together. The associative property of matrix additions allows you to write expressions such as A plus B plus C without ambiguity because the same sum occurs no matter how the matrices are grouped. The same reasoning applies to sums of 4 or more matrices. So if I'm just adding a whole bunch of matrices together, order is not important. Here are 0 matrices. A 0 matrix is simply a matrix consisting of all zeros. And as y'all saw earlier, adding a 0 matrix to a matrix results in no change, right? The algebra of real numbers and the algebra of matrices have many similarities. For example, if I have two real numbers, x plus a, I get b. If I have two matrices that have the same order, x plus a, I get b. Everything there is exactly the same, whether we're talking about real numbers or matrices. Multiplication, okay. This is where students tend to start having difficulties with matrices. Okay. And remember, it's always rows, then columns, right? When we're talking about the order of a matrix, we talk about rows first, then columns, correct? Keep that in mind, because that's going to come in play when we're multiplying matrices together. So by definition, if matrix A has members A sub ij, and matrix B has members B sub ij, and we multiply them together, then C sub ij is equal to A sub I1 times B sub 1j. This is just a mess. I'm not even going to go further in this. We're just going to do one. subscript, yeah. The definition of matrix multiplication indicates a row by column multiplication. So when we're doing matrix multiplication, we're going to take the row of the first matrix and multiply it by the column of the second matrix. Okay? Row by column, row by column, row by column. For the product of two matrices to be defined, the number of columns of the first matrix must equal the number of rows in the second matrix. Here's what this means. I think they have this in another slide, but it's really, really small. Let's say I have matrix A, and matrix A is a 3 by 2 matrix. We'll talk about what the matrix looks like in a minute. Then I've got another matrix, call it matrix B. Matrix B is a 2 by, I don't care, 6 matrix. The question is, can I multiply these matrices together? And here's what you have to look at. Notice this is A times B. A times B and B times A are not the same, not in matrices, okay? So as I write down the dimensions of A and B, I look right here. If those two numbers are the same, then I can multiply. Okay? 2 and 2, are they the same? Yes. So this can be multiplied. What about the 3 and the 6? Let me change colors. The answer order is 3 by 6. I'm going to take a 3 by 2 and multiply that matrix by a 2 by 6, and my answer is going to be a 3 by 6. That makes sense? If I took the same two matrices and I said, well, what's B times A? You would say cannot be multiplied. Okay, can't do it. Y'all feeling okay about this so far? Okay. Okay, now here's the picture. I said it's kind of messy here. So if the middle two indices are the same, then we can multiply them. The outside two indices give the order of the product as shown below. So, and there's a beautiful example. It's terrible. Let's look at numbers. I want to find the product of AB. Okay. What are the dimensions of matrix? I'm sorry, what is the order of matrix A? 3 by 2. What is the order of matrix B? Can I do this? In this order, I can do this. Okay. So I'll look at it here. Nice. It says yes. And the answer is going to be all right. All right, here we go. Rows by columns. Okay. This is row 1. This is column 1. I have -1 times -3 plus 3 times -4. that is going to be row 1, column 1 in my answer. Okay. I'm now going to take row 1 with column 2. So I'm still in row 1 in my answer, but I'm now in column 2 in my answer. What's it going to be? Well, -1 times 2 plus 3 times 1. Questions so far? I'm done with row 1. We'll now move on. Row 2, column 1. You tell me. Four times -3 plus times -4. Now I'm going to stay with row 2 and switch over to column 2. So I have 4 times 2 plus -2 times 1. Finally, row 3, column 1. 5 times -3 plus 0 times -4. Row 3, column 2. Times 2 plus 0 times 1. Now we just need to do all this math. Any questions so far? Okay. So this right here, that's -12. 3 plus -12 is -9. -2 plus 3, -12 plus 8, minus 2, -15. Who cares? 0. 10, 0. Is that a 3x2 answer?
Yeah.
That's how you multiply. Okay. It's not hard. It's tedious. It's tedious. And you've got to concentrate on what you're doing. Rows by columns, rows by columns. Okay. What row am I multiplying? What column am I multiplying? That'll tell you which cell that you were in. Okay. Questions? So you're all experts at this, huh? Same thing we got, except not as colorful. Okay, matrix multiplication. That was addition. This is multiplication. Multiplication, associative property holds true. Distributive property holds true. Both directions. I do want to point out that order is important. Notice that when we have A times B plus C, the A is in front of the B, the A is in front of the C, right? If I put C at the end, it's not B times A, is it? A is on the left. So it's A times C, B times C. Remember, for multiplying, order is important, right? Sometimes you can't do it. An associative property for a scalar holds true as well. Here's the identity matrix. I've already talked about it. Identity matrix must be of dimensions n by n. Ones on the main diagonal, zeros everywhere else. Identity matrix must be square. If you take a matrix and multiply it by the identity, you get what you started with. That's why it's called the identity. Identity matrix is always square, meaning it's n by n, in this case 3 by 3. So if I have a 3 by 3 and a 3 by 3, can I multiply them together? If I switch them, can I multiply them together? Okay. Only because one of them is the identity do I get the same answer. If I had a 3 by 3 and a 3 by 3, A times B and B times A aren't going to be equal. Did you see that property? Did you see the commutative property? Do you see a commutative property? No. Did we have one for addition? Adding matrices. Does order matter? Order doesn't matter when adding. Does order matter when multiplying? Yes. You will get two different answers. Okay? I can take a system of equations and write it as a matrix equation. And this is what it looks like. Here's the system of equations. And here's what it looks like as a matrix. Notice the constants, basically that's just a matrix. This would be your coefficient matrix here. And this right here would be your variable matrix. Okay. And this obviously is going to be your constant matrix. I've already said that. The column matrix B is also called the constant matrix. The entries in the constant terms in the systems of equations. Okay, here is a system of linear equations. Part A, write this system as a matrix AX equals B. All right, so part A. What are my coefficients? Just 1, -2, and 1. Okay, next row. Next row. Okay, so that represents my coefficient matrix. X represents my variables. My variable matrix would be X sub 1, X sub 2, X sub 3, or X, Y, Z, whatever they happen to be. Equals my constant matrix. There you go. That's part A. I have written this as a matrix equation. Now it says use Gauss-Jordan elimination on A, B. Notice it's ignoring the X, isn't it? Because by using Gauss-Jordan, what's happening is we're going to change my coefficient matrix into what? Using Gauss-Jordan, coefficient matrix becomes what matrix? Go say it. I think you're about to. No. It's going to turn all these into ones, the identity. So by using the Gauss-Jordan, I thought you were about to say it. By using Gauss-Jordan, we're going to change this matrix into the identity, and it's going to change these numbers into the solutions, won't it? Okay. All right. Okay. Here's the augmented matrix that we could use to do the Gauss-Jordan. I'm moving on. After performing, I'm not going to spend the time going to another problem doing Gauss-Jordan, but after doing the Gauss-Jordan elimination, we come up with the identity on the left side, solution matrix on the right side, which means x1 is -1, x2 is 2, and x3 is 1. So by doing the Gauss-Jordan, we have solved the system of equations. And folks, that's it for 10-2.